Bismillahirrahmanirrahim. Assalamu alaikum students. Hope you are all fine and enjoying your life with your family. Class, this is our 14th lecture. We are slowly and gradually moving towards the end of this course of operations management, and let's have a recap what we discussed in the last class. In the last class, we discussed a very important method, that is simplex method, and I told you that we can use further two techniques of solving the problems by using this method of simplex technique. That is, one of the method was bigger method, which we used in solving the problem in our last lecture, and the other method is two-phase method. We will use this two-phase method in our today's lecture in order to solve the similar problem. But let's discuss different steps which are involved in bigger method while we solve the problem of linear programming by using that simplex method. Again, class, will have to first convert the scenario or the information available in the form of equations and inequalities, and then we'll have to convert these inequalities into the equalities by introducing the artificial variables, surplus variables, or the slack variables. After introducing this slack variable and the artificial and surplus variables, we'll have to find out some initial solution. But in the last class, we discussed that sometimes by finding, during the finding of that solution, we have some contradiction of some basic mathematical rules. In that particular cases, we introduce some variables which are known as artificial variables. So we'll have to introduce these artificial variables whenever we have an equation instead of an equality, and whenever we have the contradiction or violation with some basic mathematical rules or some non-negativity constant rules. So in the last class, we discussed that how we introduce these artificial variables in order to convert those equations into inequalities, and then finally we find out some initial solution after introducing those artificial variables. Then I discussed about big M method, that is the most important method in solving the linear programming problems. And what is M actually? We suppose that M is any very large quantity, and by using that M, we reformulate our objective function, and then we rewrite our objective function in some homogeneous form, and we actually reformulate our objective function as well as our equations in order to convert them and in order to enable us to formulate the first or the initial W. Then onward, the steps were always the same. That is, first of all, we formulate the initial W by putting the different coefficients of those objective function and the equations into that initial W. We will have to check the condition of optimality, and as we solved the minimization problem in the last lecture, so the criteria of optimal solution in case of minimization was that all the coefficients of objective function should be negative. If any of the coefficient of our objective function is non-negative, then it means that this initial table will not give you the optimal solution, and we'll have to actually reformulate our table. Then again, after checking out this condition of optimality, we'll have to identify the pivot column, and pivot column is that column which is the corresponding column to the most positive value in the coefficients of objective function. So after identifying our pivot column, we identified pivot row, and by calculating the ratios by dividing the right hand side values with respect to the respective values in that pivot column. After identifying the pivot row, we find out the pivot number, that is the number of intersection of the pivot row and the pivot column. Then again, this pivot column and pivot row helped us to identify that what is your leaving variable and what is your entering variable, and by using this exchange of leaving variable with entering variable, we formulated another table, and again we repeated these steps. All of these steps were repeated until we reached some optimal solution. And again, this step-by-step procedure is sometimes referred as the process of iteration. This is actually a loop, and we will continue to conduct these loops as far as we will have the objective function and we are able to maximize or minimize our objective function. This method is also sometimes referred as algorithm, which means a step-by-step approach of solving the similar problems. So class, this was a brief recap what we discussed in the last class. And again class, जब आप शुरू में स्टार्ट करेंगे इन प्रॉब्लम्स को सॉल्व करना, तो समटाइम्स ये थोड़े से कंफ्यूजिंग आपको लगेंगे, बिकॉज इट इन्वॉल्व्स सो मैनी स्टेप्स एंड समटाइम्स द कैलकुलेशंस आर इन्वॉल्व्ड. और अगर आपकी कोई कैलकुलेशन गलत हो जाती है तो अगेन यू विल हैव टू रिपीट द क्वेश्चन. बट आफ्टर यू गो थ्रू वंस और ट्वाइस for the similar questions, then you will start enjoying solving these problems. Again class, the importance of these problems and this process of problem solving actually helps us a lot in finding out the very important decisions in the organizational setting, and we can always optimally decide about the various factors which are being faced by the organizations, and we can always maximize our profit or we can always minimize our cost, and of course we can maximize or minimize our objective function within the constraints, within the limitations of the organizational settings. So important is the technique of linear programming. Again class, this is our lecture number 14, and in today's class I will tell you about another method of simplex technique, that is known as two-phase method. As this word shows that this sort of method includes two phases. First of all, we will go through the first phase and then we will enter into the second phase, and we'll just discuss that how we can solve the similar problems by using that two-phase method. Class, I am taking here the same example which we solved last time by using that big M method. That is, we'll have to minimize our objective function, and our objective function is f is equal to 4x1 plus x2, and this function is again subject to the different constraints. And what are these constraints? That is 3x1 plus x2 is equal to 3. The second constraint is 4x1 plus 3x2 is greater than or equal to 6. Third constraint is x1 plus 2x2 is less than or equal to 4. And again we have the non-negatively constraint, that is x1 x2 is greater than or equal to 0. So again class, this in order to convert these inequalities into the equalities, we will have to introduce the slack variables and surplus variables. Let S1 and S2 be the surplus and slack variables for the second and third constraints respectively. Now this procedure is almost same which we have already done in the last example, and in case of equation we will not introduce any slack variable or surplus variable. That is, if we have a constraint in equation form, we will not initially introduce any slack variable or surplus variable. Slack variables and surplus variables are always introduced for the inequalities, which represents actually our constraints. So again, when we have less than equal to form of inequality, we will add the slack variable, and whenever we have the inequality in greater than equal to form, we will minus the surplus variable. So our second constraint is now converted into actually the equation, that is 4x1 plus 3x2 minus s1 is equal to 6. And similarly, our third equation is now x1 plus 2x2 plus s2 is equal to 4. So now these are the three equations. Now class, we will have to find out again some initial solution, and for finding out that initial solution, we again use some arbitrary values, and we find out that what is the number of variables and what are the number of equations available. As you can see that we have 4 variables, that is x1, x2, s1 and s2, and we have 2 equations. So 4 minus 2 is equal to 2. Again, it gives you the hint that we will have to put the value of 2 variables equal to 0. So that will help you to find out the values of other variables. Again class, if you use this sort of rules, तो आपको कभी भी कोई प्रॉब्लम नहीं होगी. अगर आप इसको हाइपोथेटिकली सॉल्व करने की कोशिश करेंगे तो आपको प्रॉब्लम होगी, बिकॉज समटाइम्स यू हैव मोर इक्वेशंस एंड द वेरिएबल्स, एंड समटाइम्स if you put the values of these variables equal to 0, even then you may not find the values of all the variables. But if you follow this particular rule, then it will always help you to solve these problems in a smooth fashion. So in this particular problem, we will put x1 is equal to 0 and x2 is equal to 0 in all of our 3 equations, as well as in the objective function. So our objective function will become f is equal to 0. By putting this value of x1 is equal to 0 and x2 is equal to 0, we will get the first equation in the form as 0 is equal to 3, which is again a contradiction. We have already discussed in the last class about this contradiction, that this is against the mathematical rule. Again, by putting this value in the second constant, we will get the value of s1 is equal to minus 6. Against it is against the rule of our non-negativity constant, because the value of s1 cannot be negative. So class, whenever we have these sort of situations that we have some contradiction or some violation with respect to the some basic rules, then we'll have to find out, or we'll have to introduce some other variables. This situation cannot be called as initial feasible solution, because it is not satisfying the condition. Again, that is not satisfying actually the basic rules of mathematics, so we cannot find the initial solution at this particular stage. In order to make it feasible, we need to add the artificial variables in the equations having contradictions and violations. So class, as we discussed in the last class also, that we'll have to introduce some artificial variables in order to deal with these contradictions and violations. So let a1 and a2 be the artificial variables for the first and the second equations respectively. Again class, we will introduce the artificial variables only for those equations which have some contradiction or some violation, because we were having the contradiction and violation in our first 2 equations. So that's why we have introduced the 2 artificial variables for our 2 of the equations. So now our constraints will take the form such as 3x1 plus x2 plus a1 is equal to 3, then 4x1 plus 3x2 minus s1 plus a2 is equal to 6, and the third equation is x1 plus 2x2 plus s2 is equal to 4. So now we have 6 variables, that is x1, x2, s1, s2, a1, a2, and all of these variables should be greater than or equal to 0, and this is again our non-negative constraint. Now class, from this stage and onward, in order to solve the problems, we can use the 2 methods, and these methods are referred as penalty method. Penalty method is also known as M method or big M method, and the other method is known as 2-phase method. We have already discussed the penalty method or big M method in our last class, and we solved this particular question by using that big M method. Again, here the M is a very large positive value. So we have already done with that M method. Now we will solve this particular problem by using that two-phase method. Okay class, first of all we will have to solve the problem by entering into the phase 1, and what are the different steps and what are the different approaches we will use in phase 1. That is very important to be noted. In phase 1 we will introduce the artificial objective function capital F. So class, up till now we have introduced the artificial variables for our constraints, but now in this particular phase we will introduce an artificial objective function. Initially we were having only one objective function, but now we will introduce ourselves a new objective function that is represented by capital F, and it will be equal to the sum of the artificial variables introduced in the constraints. So what will be the value of that new artificial objective function? Its value will be equal to the sum of the different artificial variables we have already introduced in order to convert our inequalities into the equalities, and in order to deal with the contradiction and violation. So we substitute the values of the artificial variables from the constraints and get the artificial objective function. Now what we will do, we will calculate the value of artificial functions which have been introduced in our equations, and then one by one we will put these values of artificial variables in the objective function. We will simplify this objective function again. We will convert it into some homogeneous form. So this is the new step which is now being introduced in this phase 1. That is, we will have to introduce an artificial objective function which will be equal to the sum of the two artificial functions which we have already introduced in our equations. And again, by calculating the value of artificial functions from our equations, we will put these values in the objective artificial function, and we will convert into some homogeneous form. So class, we have two artificial variables, so the artificial objective function would be as under, as we have already introduced the two variables, a1 for our first constraint and a2 for our second constraint. So the value of this artificial objective function, which is represented by capital F here, will be equal to the sum of a1 will be equal to the sum of a1 and a2, that is the sum of the two artificial functions. So class, as you know that this is our first equation, that is 3x1 plus x2 plus a1 is equal to 3, in which we introduced our artificial variable a1. So what we will do, we will calculate the value of a1 from here. That is, a1 will be equal to 3 minus 3x1 minus x2, and we will put this value of a1 in this new objective function. So the value of a1 from our first equation is 3 minus 3x1 minus x2. Similarly, we will calculate the value of our second artificial variable from the next equation, that is equation number 5, and we will get the value of a2 as 6 minus 4x1 minus 3x2 plus x1. So now what we'll do, we will put these values of a1 and a2 in our new objective function. Our new objective function is, that is actually the artificial objective function, capital F is equal to a1 plus a2. So we will put the values of a1, a2 we just computed here in this artificial objective function, that is capital F is equal to 3 minus 3x1 minus x2, that is the value of a1, plus within brackets 6 minus 4x1 minus 3x2 plus x1, this is the value of a2. Now what you will have to do, you will have to open out these brackets. solve these equations, and finally we can get the value of our artificial objective function as 9 minus 7x1 minus 4x2 plus s1. So this is the simplified form of our new artificial objective function. Now class, let's review the new form of our objective functions and the different equations we have in the form of the different constraints. Now we have two functions. One function is our original function, which is represented by small f, and this is equal to 4x1 plus x2, and our new artificial objective function which we introduce ourselves in this method, that is capital F is equal to 9 minus 7x1 minus 4x2 plus x1 plus s1, and all of these objective functions are subject to the different constraints. And again we have these three constraints with some non-negativity constraints. Now students, we are in a position to find out the initial solution by using that two-phase method, and please remember that still we are in the phase number 1 of this particular method. So again we will use the same approach and rule, that what is the difference between the number of variables and the number of equations available. Again, in this particular case we have 6 equations, that is x1, x2, s1, s2, a1, a2, and we have 3 equations. So 6 minus 3 is equal to 3. Now this 3 shows that we'll have to put the values of 3 variables equal to 0, and then we will be able to find the values of other variables. We are putting the values of x1, x2 and s1 to 0. So by putting all the above values in our objective functions and equation number 4, 5 and 6, we will get the value of capital F, which is again our artificial objective function. The value of this artificial objective function will become 9, and the value of our original objective function, that is small f, is equal to 0. We will get the value of a1 equal to 3, the value of a2 is equal to 6, and the value of s2 is equal to 4. So this is our initial solution. This solution is called initial feasible solution because it satisfied all the non-negativity constraints and also do not have any contradiction or violation. So students, we have adopted and we have introduced the artificial variables, as well as we have also introduced the new objective function. So this is the method to be followed in this two-phase method, and it will help us to deal with again the contradictions and violations, and it will help you always to give some initial solution free of these contradictions and violations. So what we'll have to do in the next step, again in the same fashion as we have solved the similar problems in our last lecture, we'll have to tabulate and we'll have to formulate our initial tableau. And again, in the initial tableau there are some basic variables and there are some non-basic variables. In this particular case, our basic variables are a1, a2, s2. Now again class, let me recall that our basic variables are those variables whose value we did not put equal to 0. We only put the values of x1, x2 and s1 equal to 0. So these will not be our basic variables. That's why we put a1, a2 and s2 under that column of basic variables. Then again the original objective function, and also there is another additional function we will write in this particular table, that is capital F. So we'll also write this artificial objective function here in this initial tableau. On the upper row we will have the value of x1, x2, s1, s2, a1, a2. Then again we'll have the right hand side. Now what we will do, we will put the coefficients of all of the equations as well as the functions into this table, and again we'll have to convert those objective functions in the homogeneous form. That is, we'll have to put all the values in the right hand side of those objective functions to the left hand side, so that we can get only a constant value on the right hand side, and that is the way to write all of the equations in the homogeneous pattern, so that we can use this method of tabulation in order to solve the problems. So in the first row we will put the coefficients of the first equation, and what will be the first equation? That is 3x1 plus x2 plus a1 is equal to 3. Again, in this particular equation the value of s1, s2 and a2 will be equal to 0, because there is no s1, s2 and a2 in this particular equation. Again, we will put the coefficients of second equation, that is 4x1 plus 3x2 minus s1 plus a2 is equal to 6. Again, in this case s2 and a1 will be equal to 0, because there is no s2 and a1 in this particular equation. Our third row will be in that form, which is actually the coefficients representing the third equation, that is x1 plus 2x2 plus s2 is equal to 4. Again, the values of s1, a1 and a2 will be equal to 0 in this particular case. Our objective function values will be minus 4 and minus 1 against that coefficients of x1 and x2 respectively. All the other values will be 0. The values of our artificial objective functions with respect to the specific coefficient of x1 and x2 will be 7 and 4. Again, the coefficient value of s1 in this artificial objective function is minus 1, so we will also write minus 1 here. And again, the right hand side in this particular case will be equal to 9. Again, students, I am telling you that we have to put the coefficients of this objective function and also the artificial objective function by converting them into some homogeneous form. And what is the method of converting them into the homogeneous form? That we will let only the constants on the right hand side, and we will take all the other variables on the left hand side of the equation, so that we can have an homogeneous form of objective function, and then we will be able to put those coefficient values in this particular table. So be very careful about placing the different coefficients in this particular table, because this is a very initial table, and if you wrongly put the values in this particular table, that will continue up to the end of the problem, and of course you will not be able to find out the optimal solution. So be very careful by putting those coefficients in this particular table. Now class, again we'll have to check out whether this table will give us the optimal solution or not. Again, in this artificial function of minimization, we select the maximum positive as the entering variable, which is x1. So what is the condition of optimality in this particular case? That is the case of minimization, that all of your coefficients of the objective functions should be equal to negative. If there is a single positive value for your objective function, then it means that this particular table will not give you the optimal solution. Again, as we have already introduced an artificial objective function, so we'll also check out this optimality condition for this artificial objective function. In this particular case, the values of the artificial objective function against the coefficients of x1 and x2 are 7 and 4, which are positive. So it means that this table will not give you the optimal solution. So again, class, in the next step we'll have to find out the pivot column, then we'll have to identify the pivot row, then the pivot number, and then we'll have to identify the leaving variable and the entering variable. Now this process is almost similar as we already did in the last class. So how we can identify the pivot column? the pivot column is that column which is corresponding to the highest positive value of the coefficient of artificial objective function. So students, you can see that the values of artificial objective function in this particular row are 7, 4, -1, and the highest positive value is 7. So this will be our pivot column, that is highlighted in yellow. So this will be our pivot column. After identifying the pivot column, what we will do, we will have to divide the values of this right hand side column by the corresponding value in that pivot column. That is, we will have to divide this 3 with respect to the corresponding value of that pivot column, which is also 3. So 3 divided by 3, that will be equal to 1. Again, we will divide this value of 6 in the right hand side with the corresponding value of pivot column, that is 4. So 6 by 4, that will become 1.5. Next, we'll have to divide this 4 again by the corresponding value of the pivot column, which is 1. So 4 by 1 will be equal to 4. In next case, if we divide this 0, that is the value in the right hand side, by that -1, so in this particular case we will get the infinity, because according to the mathematical rule, if we divide the 0 by any number, we will get the infinity. So we have already discussed that when we are going to calculate these ratios, then we will ignore the negative values as well as the infinity values. We will always take into account only the positive values. So in this particular case, we will ignore this value. Then again, in the next row, if we divide this 9 by 7, we can get another value of that ratio, but that is not being required here, so that is not being calculated here. So class, again we'll have to find out the minimum ratio out of these 3 available ratios. In this particular case, the minimum ratio is 1. So this minimum ratio 1 actually helps us to identify the pivot row. So this is our corresponding pivot row, which corresponds to the minimum ratio value, that is 1. So this is our pivot row. The next value we'll have to identify, that is again a very important value of pivot number, and again we'll have to identify the point of intersection of the pivot column and the pivot row, and the corresponding value will be your pivot number, which is actually 3 in this particular case. Again, this value 3 is the intersection of pivot column and pivot row. So we have identified the pivot row, we have identified the pivot column, we have also computed and identified the pivot number. Next, what we'll have to do, we'll have to identify our leaving variable and our entering variable. Our entering variable will be the respective non-basic variable which corresponds to the highest most value of the coefficient of our artificial objective function. Or we can also say that the value of non-basic variable, that is x1 in this particular case, which corresponds to the pivot column. So in this particular case, the x1 will be our entering variable. Again, the basic variable which corresponds to the pivot row, that is a1, will be our leaving variable. So x1 is our entering variable and a1 is our leaving variable. Now why it is important to identify this leaving variable and entering variable, because when we will make and formulate the next table, then we will have to replace these values. That is, we will have to replace this artificial variable, which is actually the basic variable a1, with respect to that non-basic variable x1. So we will put x1 in place of a1 at this particular position when we will formulate our next table. So let me repeat the criteria of optimality, that is the solution of artificial objective function is said to be optimal when artificial objective function coefficients become non-positive or zero, and that is the case for the minimization problems. Again, the case for the maximization problem may be different, because in case of maximizing the objective function, we are interested, and our condition of optimality is that the coefficients of objective functions should be positive. But here in this particular example, we have to minimize our objective function, so we are interested, and the condition of optimality in this particular condition is that the coefficients of our objective function, and especially here at this particular stage, the coefficients of artificial objective functions should become non-positive or zero, and if this condition prevails, that will give us the hint that this table can give you some optimal solution. So again class, as in the initial table, we didn't meet the criteria of that optimal condition, so we'll have to reformulate another table. And again class, while reformulating the table, you'll have to remember two important formulas. One formula is for the new pivot row calculations, and the other formula is for all the other rows which are actually other than the pivot rows. The formula is different, and the formula for the new pivot row is equal to 1 over pivot number, that is old pivot row, as we have already identified in this particular table that our pivot number in this particular case is 3, that is the intersection of this pivot row and pivot column. And again, our pivot row in this case will be 3 1 0 0 1 0 3. So we will put these values here. 1 over 3, that is the pivot number, as 3 multiplied by these values of old pivot row. So it is always good to write these rows in this particular style, so that there are minimum chances of miscalculation. As I already have told you that a lot of calculations are involved in these sort of problems, so it is always good to represent and to present actually your solution in a manner that there are least chances of miscalculation. So if we multiply this value of 1 by 3 by each value of this old pivot row, we will get the new pivot row as 1 1 by 3 0 0 1 by 3 0 and 1. Now students, let me again clarify that we'll have to multiply this particular value by each value of this old pivot row, that is 3 multiplied by 1 by 3, this will be equal to 1. So we'll have to write 1 here, then 1 multiplied by 1 by 3, this is 1 by 3, 0 divided by 3 is equal to 0, again 0, then 1 over 3, then 0, and then again 3 by 3 is equal to 1. So in this particular case, we will find the new pivot row. Now in the next stage, we'll have to find out the other new rows, that is the other than pivot rows. That is, the formula used for this particular objective is old row minus pivot column coefficient into new pivot row. We'll have to find out the new A2 row, and again the same formula will be used, that this will be equal to old A2 row minus pivot column coefficient. Now again class, if we refer the old A2 row in this our initial table, then this is the A2 row and this is our pivot column. So our corresponding A2 row coefficient is 4. So that's why we put that 4 there in that formula. So our new A2 row will be equal to old A2 row minus this pivot column coefficient, that is 4, into or multiplied by new pivot row. So this is our new pivot row. again by solving one by one all of these values, we will get the new A2 row as 0, 5 by 3, minus 1, 0, minus 4 by 3, 1 and 2. Then again we will have to calculate the new S2 row, and the same formula will be used, that is new S2 row is equal to old S2 row in our previous table minus corresponding value of pivot column coefficient, which is actually 1 in this particular case, multiplied by new pivot row. So these are the values of new pivot row. So again by solving one by one all of these values, we will get the new S2 row equal to 0, 5 by 3, 0, 1, minus 1 by 3, 0 and 3. In the same way, we will have to compute our new small f row. This will be equal to our old small f row, which is actually our old objective function or our original objective function, minus the corresponding value of pivot column coefficient into again the new pivot row. So by solving again one by one all of these values, we will get the new f row as 0, 1 by 3, 0, 0, 4 by 3, 0 and 4. As we have another function which is actually the artificial objective function, which we introduced on our own by using this method which is referred as two-phase method. So we'll have to find out the new capital F row as well. So the same formula will be used to calculate the new capital F row, that is it will be equal to the old capital F row minus corresponding pivot column coefficient multiplied by new pivot row. So again class, 7 minus 7, it will become 0. Then again 4 minus 7 multiplied by 1 by 3, it will become 5 by 3, minus 1 plus this will become 0 and this will become minus 1. So again in the same manner, by solving all of these corresponding values, we will get the new capital F row as 0, 5 by 3, minus 1, 0, minus 7 by 3, 0 and 2. So these are very important formulas class, and again I am telling you to be very careful when you are calculating these values, because mostly it happens that if there is something wrong in this calculation, and then again this wrong calculation will let you go up to the end of the problem, and of course at the end you may not find the optimal solution. So please have a double check when you are going to calculate these values in order to avoid any problem for solving these questions. So class, after we have computed the pivot row and all the other rows required, what we will do, we will have to compute and formulate another table by putting all of these newly computed rows at their respective places. So first of all, what we will do, we will place this new pivot row at the position of this old pivot row. So this is our new table, and here we have put that new pivot row in exactly similar position of old pivot row, and again all the other rows which we have computed other than pivot row will be placed at their corresponding positions. So in this way again we have a new table, and again we will have to follow the similar step, that is we have to check the condition of optimality, that is whether the coefficients of our objective function are positive or not. But in this particular case, as we are interested in minimization problem, so all of the coefficients of our objective functions should be negative. If there is a single coefficient of objective function having the positive value, then we'll have to again reformulate our table. So if we see the values of our artificial objective function, there is one positive value in this particular row of our artificial objective function, that is 5 by 3, it means that this is not the optimal solution, and we will have to formulate yet another table. And again, class, we will repeat the similar steps. That is, first of all, we will have to find out the maximum number in that row of artificial objective function. As you can see that the maximum value or the maximum positive value in this artificial objective function is 5 by 3. So this particular column will be our pivot column in this particular table. After identifying the pivot column, we'll have to identify the pivot row. For that particular reason, we'll have to calculate the ratios. That is, we'll have to divide again the values in that right hand side column with respect to the corresponding values in the pivot column. So 1 divided by 1 by 3, this will be equal to 3. Again, the 2 divided by 5 by 3, this will become equal to 1.2. 3 divided by 5 by 3, this will be again 1.8. Then again we can calculate the ratios for small f and capital F, but again there is no usage of calculating these ratios, so we have omitted this particular step here. Now we'll have to find out that what is the minimum value of ratio we have just computed. In this particular case, the minimum ratio value is 1.2. So the corresponding row with respect to that minimum ratio value will be our pivot row. So this is our pivot row, and our pivot number is 5 by 3 because that is the point of intersection of pivot row and pivot column. So our pivot number will be equal to 5 by 3. So in the next step, we'll have to identify what is our entering variable and what is our leaving variable. In this particular case, x2 will be our entering variable, which actually corresponds to the relevant pivot column, and in this case the a2 variable will be our existing variable or our leaving variable, which corresponds to the relevant pivot row. So x2 is our entering variable and a2 is our leaving variable. Again, what is meant by this or what is the purpose of identifying this entering variable and leaving variable? We'll have to replace this a2 by x2 when we will formulate the next table. So after identifying all of the values of pivot column, pivot row, pivot number, then entering variable and leaving variable, we'll have to compute another table in order to find that optimal solution. And again, students will have to use the same formula, that is the new pivot row is equal to 1 over pivot number multiplied by old pivot row. By using this particular formula, we'll have to again find out our new row for the next table. In this particular case, that is if we refer to the previous table, our pivot number is 5 by 3. So the formula for our new pivot row will be equal to 1 over 5 by 3 multiplied by the old pivot row. So again, if we compute the values for all of these old pivot row values, we can get the new pivot row values as 0, 1, minus 3 by 5, 0, minus 4 by 5, 3 by 5 and 6 by 5. So these are the values for our new pivot row. And again, when we will formulate the new table, we will first replace this new pivot row with the old pivot row. Similarly, by using the formula for the other rows which are not actually our pivot rows, we will have to calculate the values of all the rows required. And again, the formula used will be old row minus pivot column coefficient multiplied by new pivot row. So by using this particular formula, we can calculate the new x1 row values, that is old x1 row values minus pivot column coefficient multiplied by new pivot row. So by again calculating and solving these particular values, we will get the values of new x1 row as 1, 0, 1 by 5, 0, 3 by 5, minus 1 by 5, and 3 by 5. Next is the value for our new S2 row. In the same way, you can always calculate the new S2 row as well. Similarly, we'll have to calculate the values for our new small f row, which is actually our original objective function, and new capital F row, and capital F here is again our artificial objective function. So after calculating all of these row values, we'll have to replace these row values in our new table. So after putting all of these values in this new table, again we'll have to check the criteria for optimality. Now in this particular case, there is no positive value in the artificial function, so this is the end of phase 1. So class, again our criteria for optimal objectivity is that all the values of our objective function, which is actually capital F in this particular case, they should always be non-positive. So all of the values you can see from this table, all of the values for artificial objective function are non-positive. So it means this table will give us the optimal solution, or that is the end of our phase 1, and this is the point in which or at which we will enter into the phase 2. As I told you that again this method is usually referred as two-phase method, and still we are in the first phase. Now this is the end of the first phase, and now we'll move to the second phase. But what we will do for moving to the second phase, that is important. Now class, by entering into phase 2, what we will have to do, we'll have to omit that artificial objective function from this particular table, as well as we'll also have to omit the artificial variable functions, that is the non-basic variables in this last table we have computed in the phase 1. So we will just cross and we will just ignore these values of artificial objective function and the two artificial functions or artificial variables, that is a1, a2, and in the similar fashion. So in this phase 2, we'll have to rewrite the previous W by dropping the artificial objective function and artificial variables. So we will have to drop 3 variables in this particular case, that is the new artificial objective function, that is represented by f. So the corresponding row will be deleted, or we will drop it, and the corresponding columns of the artificial variables, that is a1 and a2. So again we will drop these 2 columns a1 and a2, and again we will reformulate another table. So this is our new table by dropping that artificial objective function and the artificial functions a1 and a2. Now from this stage onward, again we'll have to follow the similar steps, that is we will have to identify that whether this table will give you the optimal solution or not. So again you can see from the coefficients of this objective function that there is still a positive value in this objective function, that is 1 by 5. So it means that this table will not give you the optimal solution, and now we will have to identify again the pivot row. As the maximum available positive value in this objective function is 1 by 5, so this is our pivot column in this particular case. Again you'll have to identify the pivot row by calculating the ratios, that is you'll have to divide that right hand side values with respect to the corresponding values of pivot column. So after calculating these ratios, we'll have to find out that what is the minimum ratio, and in this particular case 1 is the minimum ratio and the corresponding row will be your pivot row. So class, again we'll have to identify the pivot number as well, that is the point of intersection of pivot row and pivot column, and again in this particular case S1 will be our entering variable and S2 will be our leaving variable, that is being represented by the corresponding pivot column and pivot row. So after identifying all of these pivot number, leaving variable and entering variable, we'll have to reformulate again the table, and for this purpose we'll have to again calculate the new pivot row and all the other rows other than the pivot row. now you are well aware of using these formulas, and you can easily calculate all of these values for the pivot row and the non-pivot rows. So the same formulas are used for these calculations, and again after computing all of these row values, we'll have to put these particular values in the new table. So this is our new table, and again we'll have to check out the condition of optimality. As you can see in this particular table, that there is not a positive value coefficient in that particular row of our objective function. So this gives you the idea that our condition of optimality is being satisfied. So this table gives you the optimal solution. And what is the optimal solution actually? The value of x1, which is being written to the corresponding cell of right hand side, that is x1 is equal to 2 by 5 and x2 is equal to 9 by 5. So if we put these particular values in our objective function, that is small f is equal to 4x1 plus x2, we will get the value of our objective function as 17 by 5. So class, in this way what we do, we use that second method of simplex method, that is two-phase method, and finally again we are able to find the optimal solution. That is, if we put x1 equal to 2 by 5 and x2 equal to 9 by 5, we will get the maximum value of our objective function, which is 17 by 5. And this value is same as we computed in the last lecture by using that big M method. So this is all about the two-phase method of solving the linear programming problems. So again class, I would say that all of these steps, whether it is the big M method or whether it is the two-phase method, you should always have these steps on your fingertips, and so that you will be able to find out the optimal solution. So class, today we discussed about the two-phase method of simplex problems, and again we repeated the similar steps, as well as we introduced some new steps. That is, we introduced the artificial objective function in this particular method, and again all the other steps are almost same, which we have already used in our previous method. So it is very important for you students that you should take some similar problems, and you should solve these problems by the big M method as well as by this two-phase method, so that you have much of the practice that how to solve these problems, how to formulate and reformulate the tables, and how to check the criteria of optimality, and of course at the end you should be able to find out the optimal solution. So this is all about our today's lecture, and there will be one more lecture for that simplex method, and in that particular lecture we will just discuss the different problems, that what are the different situations in which we cannot have some optimal solution by using these sort of methods. So we will discuss some cases in the next class. Okay class, thank you for your patience. Khuda Hafiz.